Good morning. Welcome back to the Wednesday session of the conference. Our first speaker today is Xie Chen from Caltech. He's going to tell us about line defects of 2 + 1D critical points.
Thank you. It's really a great pleasure to be here because I've been working on this invertible categorical symmetry topic for only maybe a little more than a year. And this is, I think, the first formal symmetries, generalized symmetry conference I've been to. So this is an opportunity for me to get to know a lot of people who are actively already contributing to this field for decades, and to put faces to names and to papers. So it's very exciting for me, and an opportunity for me to also tell you about what we are thinking about using non-invertible symmetries and all these categorical language, and what I in particular try to learn using this framework. So I am a condensed matter theorist, and my motivation, of course, is in large part just to study phase and phase transitions. And in particular, I think from my perspective, this whole topological holography, symmetry TFT language, I'm hoping to learn about two things from it. One is 3 + 1D topological order, and the other one is 2 + 1D critical point. Of course, they will be related to each other through this bulk boundary correspondence, and I think I'll be really excited if I learn new things, learn proper language and new perspective and deeper insights into these two things. Of course, these two, they're both very difficult topics, and but through this topological holography framework, I see a very tight connection between the two. So hopefully, learning about one will tell us about the other, and vice versa. Okay, so the work I'm going to talk about today is through collaboration with Wenjie. Many of you might know her, and I learned so much from Wenjie during the process. So this is our attempt to try to learn something from about 2 + 1D critical points, starting from 3 + 1D topological order. Of course, there's still a lot of open questions on both sides, but maybe some connection can already be established using the topological holography picture. So let me just get into it. And of course, I like many of the talks before, I use extensively the sandwich structure. And Zhenghan was asking me what's a sandwich 5 minutes ago. And this is, I learned it's not just for breakfast or lunch. It's some construction that allows us to make very explicit the relation between the TQFT in the bulk and a general QFT on the boundary. And I realized, as I start to learn about this very powerful framework, that there was a lot of work building up, leading to this structure, and already building on this structure over the decades. So I'm trying to bulk cite a lot of papers, but I'm sure I'm still missing many of them. So hopefully the ones on the slides covers a lot of them, but if some of them are still missing, please let me know. And I'll just give a very quick review of the basic structures of a sandwich, which I think has been talked about a lot at this conference, but then I'll delve into specific examples of how I want to use it. So the general sandwich has a D + 1 dimensional TQFT, a topological state in the bulk. So when I draw pictures, I'm drawing a spatial picture, so maybe 1 dimension lower than the picture in some other talks. So this is the spatial dimensions of the sandwich. And then so in particular, what I'm drawing is a 2 + 1D topological bulk. And then the top boundary will be gapped, so I'll put the topological boundary on the top. And then the topological bulk and the gap boundary together kind of determine the kinetic part of the system, which to most extent is just specifying the symmetry of the system. And down below, the bottom boundary is kind of left open, and that's where all the dynamics can happen, and it can be different phases or phase transitions, and that's all the interesting dynamics. And the nice thing about the sandwich structure is that it separates things out, even though there's only a finite extent in the vertical direction, but it still allows us to pull things apart. In particular, the topological, the TQFT in the bulk, there are some logical operators that runs parallel to the boundary so that it floats kind of in the middle and away from the dynamics. And that's what specifies the symmetry. It either measures the symmetry charge or measures the symmetry flux. So these topological logical operators will specify the symmetry sectors of the sandwich. And that kind of, the sandwich structure allows us to separate them from the dynamical part of the system. And then vertically, those logical operators also play a role, and the role they play is that they can tunnel things between the top boundary and the bottom boundary, such that it might cross these symmetry sector determining logical operators and change the sector. So when you tunnel a charge, it changes the charge sector. When we tunnel a twist, then a twist operator, then it changes the flux sector. Okay. So I'm going to repeatedly using this structure throughout my talk, first with a 1+1D sandwich, and then going to a 2+1D sandwich. Okay, so of course this structure is well understood and used a lot. And just as a review, as a build-up to the later examples I want to talk about, let me start from a 1+1D sandwich with a 2+1D topological order in the bulk, and in particular, I take the simplest 2+1D topological order, which is the 2+1D toric code, or maybe you like to call the Z2 gauge theory, or some other name. So I'll use all these names interchangeably. Hopefully that's not too confusing. And then the topological boundary at the top is achieved by condensing some of the anyons from the bulk. And the 2D toric code, there's a gauge charge that's a boson. So we can just condense the gauge charge on the top. So for information people, this is called the rough boundary. And the sandwich with this bulk and the boundary can be used to describe 1+1D system with global Z2 symmetry, and this is what we usually call a 1+1D Ising chain. And the symmetry determining operators are the large horizontal string operators in the bulk. For example, the string operator of the E charge running horizontally measures the flux sector of the system, while the M string operator running horizontally measures the Z2 symmetry, the global Z2 symmetry. And then tunneling E vertically will anti-commute with the M string operator in the horizontal direction, and therefore changing the charge sector of the sandwich. On the other hand, if we tunnel an M particle in the vertical direction, it will change the flux sector. So this is how we specify the sectors and how we can commute all these sectors. Okay. Yeah, and then we can start talking about what can happen on the bottom boundary. And the bottom boundary, we can do something simple. For example, we can again condense the E particle. And when we condense the E particle, we can actually use the identification of the charge operator and the flux operator to see that if the E particle is condensed both at the top and the bottom boundary, then this charge operator doesn't cause any energy, which means that the Z2 symmetry is spontaneously broken. This is the symmetry breaking phase. On the other hand, if we condense the M particle, then the charge will cause, tunneling a charge will cause some energy, but tunneling a flux will not cause energy in the bottom boundary. So this is the other gap phase, which is actually the symmetric phase of the 1+1D Ising chain. So here when I say something condensed, I mean that you bring an excitation to this region and that excitation disappears. It doesn't cause any energy anymore. Of course, and then we can tune the bottom boundary to somewhere in between the E condensate and the M condensate so that neither of them condense. And then we go into a gapless boundary, and this can be, of course, at the transition point between these two boundaries and between the symmetry breaking phase and the symmetric phase. And this is, of course, matches well with what we have always understood about 1+1D Ising chain with a transverse field and then with a Ising coupling. And if we tune the coupling strength G, then we can be in two different phases. One is the symmetric phase, and the other, is symmetry breaking phase. And the understanding of E condense and M condense from the sandwich picture also has a correspondence in this simple spin chain picture, because in the symmetric phase, we can say that what gets condensed is the symmetry domain wall, right? Because in the symmetric phase, we see that the wave function is very simple. It's the limit where only the transverse field is here, only the transverse field. So the wave function is just a product state of spin pointing in the x direction. And now if we add try to add a symmetry flux, in the limit where G is equal to 0, sorry, I don't know why I didn't include 0. I should have included 0. And so at least at the point of G equal to 0, then the symmetry flux doesn't change the Hamiltonian at all. And the wave function remains invariant, everything remains invariant. So in that sense, a symmetry flux or a symmetry domain wall does not cost extra energy, and it gets condensed. So in that sense, it's a flux condensate. And if we move away from the exact point of G equal to 0, then inserting a flux will cost a little energy because this term is present in the Hamiltonian, so something's changed. But we can see that the change in the ground state energy goes exponentially small with system size. So when you have a very long chain, the energy difference is very, very small. On the other hand, we have the symmetry breaking phase, and it's well known that the symmetry breaking phase can be considered as a charge condensate. And the way I use the word charge condensate means that I have a twofold ground state degeneracy, being all 0 and all 1. And if I start from one of them, I add a charge. I just toggle between the plus sign and minus sign, and these two are degenerate ground states. So their energy difference is also exponentially small in the total system size. So charge is condensed in the symmetry breaking phase. And then in between, when I tune G to equal to 1, this is at the critical point. And what I'm trying to say is that these two condensate. The fact that the two phases on the two sides are, one is charge condensate, the other is flux condensate, have a lot to say about what happens at the critical point. And in particular, at the critical point, roughly we can think about this. When I learned from Xiaogang, from Wenjie, and from many previous works, that there are two things trying to condense, but at the critical point they cannot both condense because these two are not consistent condensate. So they try to compete with each other, but then none of them can consistently condense. And the resulting thing is, of course, we know that at the critical point we have an Ising CFT. And at Ising CFT, the charge and the flux each become a low energy degree of freedom. Basically, they become the primary fields of the Ising CFT. And energetically, we see that this means that they still have pretty low energy, but their energy is not exponentially small. It's only 1 over L small. It's only polynomially small. And in particular, there's a very specific coefficient in front of this 1 over L scaling, and here it's 1/8, and it's famously 1/8 for both the charge and the flux. So this is some structure that I'll try to see if we can extend to one higher dimension. Of course, here is very well understood. And another feature I'll try to extend to one higher dimension is about the modular invariance of the partition function, which is, of course, another feature that's well understood for 1 plus 1D icing. We know that for 1 plus 1D icing, the partition function has 3 parts. One is the trivial primary field, and the other is the epsilon, and the third one is the sigma. And when we add these 3 parts together, we get a modular invariant partition function. And this has a very nice interpretation, again, in terms of the sandwich structure, because in the sandwich structure, we can see how these towers fit into different sectors. So from the sandwich, we see that there are 4 sectors labeled by the charge and the flux of the Z2 symmetry. And the trivial field and the energy field, these 2 towers actually belong to the 1,1 sector, while the charge sector corresponds to the sigma field, because sigma is the spin, is the symmetry charge. And then the M sector, being the flux, of course, corresponds to the mu primary field, because that is the domain wall, the symmetry flux. And finally, we have the composite of E and M, which gives you the F anion in the bulk, and correspondingly, the sector on the boundary CFT contains the fermions, and there's a left fermion and there's a right fermion, and the sum of them give us the 4th sector. And in order to get a modular invariant partition function, what we do is actually to look at the top boundary. Okay. The top boundary tells us how to put these sectors together in order to get a modular invariant partition function. And here, because the top boundary is a condensate of E, so we're taking the first component and the second component and sum them together, and that will give us a consistently modular invariant partition function. So this is, of course, all understood within the bulk of paper I cited on the first slide, so I'm not specifically referring to papers here. And then, of course, the modular invariance of the partition function and also the low energy degree of freedom at the critical point, these will be the 2 specific aspects that I'll try to extend to one higher dimension. But before doing that, let me take one more small step, because I was talking about Ising chain, I was talking about Ising CFT, and I want to do a Jordan-Wigner to get to the 1 plus 1D fermion example before I go to 2 plus 1D, because in 2 plus 1D I also want to talk about fermions. Okay. So the second example is nothing but the Jordan-Wigner transformation of the 1 plus 1D Ising chain. And it's basically the same sandwich, it's the same bulk, topological order, 2 plus 1D toric code, but the top boundary is slightly different. The top boundary, we try to condense fermions in order to make the sandwich a fermion system, but fermions famously, they cannot just condense, so in order to condense fermions, we need to actually bring some real fermions into the system, so we add some fermion modes, and then we bring the quasi-particle from the bulk and pair them up with these physical added fermions on the boundary and pair condense those 2, and then we can get a fermion condensed boundary on the top. So I should have cited some more recent papers about this fermion condensed boundary. There's a few papers recently about how to condense fermions and get a fermionic sandwich. But then the story proceeds very similarly. There are some string operators in the bulk that measures the symmetry flux. In this particular case, it's the fermion string operator that measures the flux, and then the other string operators will give us the symmetry charge. And then tunneling anions in the vertical direction will give us the charge operator and the flux operator. So it's literally parallel stories. And then for the bottom boundary, we still have the same choice. We can condense E anyang, or we can condense M anyang, and then we can tune between to the critical point, except that now the interpretation as one-dimensional phases are different because this is now a fermion system. And we know from Jordan-Wigner transformation that one side is a trivial superconductor, the other side is actually the non-trivial P-wave superconductor, I just call Kitaev chain. And as a 1+1D fermion model, the Kitaev chain is, of course, well understood. This is the simple lattice model where you have Majorana modes, and the Majorana modes pair together. They either pair together on site or they pair together between sites. And these two limits give you the trivial and the non-trivial superconductors. And the trivial superconductor, in the previous language, we tried to describe these gap phases in terms of condensate. And in the sandwich picture, of course, it corresponds to the M condensate. And back to the 1+1D fermion model, we can still try to think of it as some kind of condensate. And I'll say that the trivial superconductor actually corresponds to condensing the Z2 symmetry flux. So we don't usually say that, but I also think this is something is also kind of understood, but we don't usually think of the transition this way because it's fermion. And what we usually say about these kind of transition is that, oh, there's a topological band structure on this side, topological band structure on that side, and index change, and there's a critical point in between. But if we, now the sandwich structure gives us a very strong hint that this is also some kind of condensate, and what is being condensed here is the symmetry flux. And again, I'll use the exactly solvable point as an illustration where the Majoranas are only paired on site, and in the limit where there's no coupling between site, then inserting a flux, of course, does nothing to the Hamiltonian. So in that sense, inserting a flux does not cost energy, so flux is condensed. And if we move away from the exactly solvable point, the energy difference will again be exponentially small. The other side is the Kitaev chain. And the Kitaev chain famously has another exactly solvable limit where the Majoranas are paired between sites. So it's just this pairing. And now if we insert a flux, things will change because that pairing will flip sign. And the whole Hamiltonian wave function changes, but it changes in a way that this particular pair of Majorana will actually flip fermion parity, right? It gains a fermion. So what we can think of that as a condensate of not just a pure flux, but a flux plus fermion. So if we add a flux and at the same time add a fermion, then the ground state wave function, the ground state energy goes back, and the energy difference will at most be exponentially small in the system size. So this is again, of course, consistent with the fact that in the sandwich picture, we say one is M condensate, the other is E condensate, because E and M differ by a fermion. And then at the critical point now is described by this free fermion theory. It's very similar to Ising with small difference. And we see again that these condensed objects on the two sides become the primary field in the theory, and they have 1/L scaling of energy with specific coefficient, and moreover, they're composite. One is the energy and the other is the left and right moving fermions, also become the primary fields with 1/L scaling with specific coefficients. Okay, so this is, and finally the partition function, the partition function now contains fermions because this is literally a fermion system, and that can be, again, understood from the sandwich picture because now the top boundary is fermion condensed. So when we try to put these sectors together, we put the identity sector and the fermion sector together, and we see that the partition function will now contain these four parts. This is not quite moduli invariant anymore because this is a fermion system, but it's some extended version of moduli invariance. Okay, so my goal is 5 minutes to talk about one dimension higher, and in particular 3+1D fermionic toric code and 2+1D p-wave superconductor on the boundary. So this is one particular example that we were able to work things more explicitly, because with a free fermion boundary theory, we can do a lot of calculations. But of course, this framework doesn't restrict to just this particular example. So we take the 3+1D fermionic toric code in the book and ask what we can learn from it about the boundary theory using the sandwich picture. So first of all, the fractional excitations in 3+1D fermionic toric code is well understood. There's a fermionic gauge charge, and then there's a Z2 flux loop, and they go around each other with a minus sign. So this is the Z2 gauge theory part. But of course, the latest development in terms of all these higher category structure is telling us that this is not the end of the story, and there's some interesting other kind of line excitations that we need to take into consideration. This is related to, of course, what Potion has been talking about yesterday, that in particular, I'm going to highlight this Kitaev chain excitation. Basically, the fermions, the quasi-particle fermions can form Kitaev chain, and that's also a line excitation. And when we talk about the flux loop excitation, actually, we can also attach to it these Kitaev chain. And it's actually not well defined to talk about which one doesn't have a Kitaev chain, which one does have a Kitaev chain. We can only talk about there are two different kinds of flux loop. Their difference being this attachment of the Kitaev chain. But the attachment of Kitaev chain doesn't affect the fact that the charge wind around it with a minus sign phase factor. So it's still a well legitimate flux loop. And that has consequence when we try to think about the sandwich structure, because that affects how we think about logical operators, how we think about the symmetry sectors, and what we can tunnel from the top boundary to the bottom boundary. Okay. So in particular, let me consider this structure where the top boundary is fermion condensed. Again, I need to add physical fermions in order to condense fermions, but let's assume that we do that. So once we fix the top boundary, then we pick which symmetry we're considering. And the symmetry here is, again, the Z2 symmetry. And this is we will turn into the fermion parity symmetry of the sandwich. And this is realized by the membrane operator of the Z2 flux. Okay. And this is the membrane operator that measures the symmetry charge. And then there are other operators that runs parallel to the boundary. And in particular, there can be these line operators that tunnels a fermion in two different directions parallel to the boundary. And those actually measures the symmetry flux of a fermion parity, a fermion system with fermion parity symmetry. Right, so now we have two flux measuring operators. And now, if we try to tunnel something in the vertical direction, it's going to change between these sectors. For example, if we tunnel a fermion charge from the top to the bottom, we're going to change the symmetry sector. And if we tunnel some membrane operators from the top to the bottom, then we're going to change the flux sector. Okay, so the string operator is the charge operator, and the membrane operator will be the twist operator, the flux operator. Right, so that's the bulk and the top boundary, and now let's start talking about what can happen on the bottom boundary. On the bottom boundary, we can do something else. Instead of condensing fermion, we can try to condense flux loops. That's the interesting case I want to look at. And in particular, since I talk about the fact that there are two kinds of flux loops, so we can actually have two different kinds of condensate. One is just pure flux loop condensate, and the other one is the flux loop together with Kitaev chain condensate. Of course, there's actually not well defined to say which one is which, but there are two, and they're relatively distinct. And identify one of them as the trivial superconductor, and the other one actually as the so-called P plus IP superconductor. And the way to understand why one is a trivial superconductor, the other one is a non-trivial superconductor is very much related to what Potion was talking about yesterday, that we can pump a P plus IP through the bulk to the boundary. And when you pump it through the bulk, it's a symmetry of the bulk, so nothing changes in the bulk. But once it goes to the boundary, it will change the boundary type, and by literally just adding a P plus IP on top. So if one side is a trivial superconductor and the other side is just adding a P plus IP and turns into a non-trivial P plus IP superconductor. And moreover, this is also related to, consistent with the fact that one side is just the flux loop condensate and the other side is the flux loop plus Kitaev chain condensate, because when we tunnel a membrane operator in the vertical direction, which generates a flux loop at the bottom, it goes through this added plane of P plus IP, and we know that a flux loop in the P plus IP actually generates a Kitaev chain along the intersection, right? So the flux loop at the bottom will be attached to a Kitaev chain because of this added plane of P plus IP. So this is why the condensate on the two sides are actually two different condensates. Okay, so this is again, of course, something we can understand from a purely 2 plus 1D perspective. So this is the lattice model we usually write down for realizing these two kinds of superconducting phases, and then we can tune some parameter to go through the phase transition. In particular, the parameter is the mu, is the chemical potential here. And on the two sides, one is the trivial superconductor, the other one is the P plus IP superconductor. And the trivial superconductor, we can think of it as, again, a flux loop condensate. This is not how we usually talk about trivial superconductor and P plus IP superconductor, but again, inspired by the sandwich construction, we see that this is a good way to think about these gap phases. Because in the trivial superconductor, we can again tune to a limit where it's just atomic limit, where every side is not coupled with each other. And then if we add a symmetry flux, which means that we want to flip signs along the green line, but because there's no coupling between the sides, so this does nothing, so the flux loop again is condensed. And we can also tune away from this exactly solvable point and calculate the energy difference before and after inserting the flux line. And we see that this is, again, exponentially small in system size. So this is a legitimate, what we call a flux loop condensate. On the other side, we have the P plus IP superconductor, and famously, P plus IP superconductor respond to the insertion of a flux line by having, basically having Majorana modes, if we, if it has endpoint. Basically meaning that the flux loop is getting attached to a Kitaev chain along its length. So something changes, but if we add another Kitaev chain, then we can undo the changes and take the system back to itself. So in that sense, we say that it's the flux loop together with Kitaev chain, this composite condensate, and we can again calculate the energy difference to be exponentially small. So I need to explain a little bit. This is actually one thing I do want to explain.
I think we need to wrap up because we actually are already 5 minutes over the actual time, including the questions.
So can I just say the result and then, I will not explain, but I'll just say the result. And the result is that, this is a nice part, but I don't get time to explain. But our result is that now we look at the critical point, which is a Majorana cone. This is all well understood, and this is a free fermion system. And we try to calculate the energy of those flux lines, including flux lines and flux lines with Kitaev chain. And we see that the energy difference goes as 1 over L. So this is similar to what we see in the 1 plus 1D case, that at critical point, these low energy degrees of freedom, which are condensed on the two sides, compete with each other. They try to be low energy, but not that low. It's 1 over L scaling of the energy. So this is, of course, something we found some other paper also did the calculation, and probably some other reference, other people also did the calculation. This is not a particularly hard calculation. But we're trying to put into this context of loop condensate, and then at the transition, these loops have 1 over L scaling of energy. So this is one part. And the other part has to do with how we put together the partition function to get a modulating partition function. So here, for this free fermion system, so from the sandwich structure, we see that there are 8 sectors, given the 8 sectors measured by these logical operators. And if we have a top boundary that's fermion condensate, we put these 2 parts together. This is the usual fermion partition function. But if we have the flux condensate at the top, then we have some different way of combining the different sectors. Actually, we have 4 parts that gets combined together. And in a paper by Xie and collaborators, they explicitly show that when these 4 parts, well, they showed it for the Dirac fermion case, but then you take the square root, and the result applies to this Majorana case, that this is, again, a modulating invariant partition function. And what's actually nice is to see that this story works if we have the other loop condensate at the top. So we make some slightly different composition of the partition function. The only difference is that previously, we have 4 sectors with even charge. Now the last sector has odd charge. But this is, again, the same modular invariant partition function for the Majorana cone, because with PP periodic boundary condition, there's a 0 mode. So the even and odd sector of the partition function actually are exactly the same. So this is, again, consistent with the fact that when we use the top boundary to determine the partition function, we get a modular invariant partition function. So that's all. Sorry, I already take more time than I should, but any questions, welcome. Thank you.
Are there any quick questions?
Okay. People can ask.
Okay. You can ask the questions during the break. Let's thank Xie Chen again.